Today I would like to show you how Aristarchus of Samos, an ancient Greek astronomer and mathematician, was able to determine the distance to the Sun and Moon by using a series of observations of the Moon and some basic geometry. Aristarchus was born around 310 BC on the Ionian island of Samos, and he studied at the Lyceum in Athens before moving to Alexandria, where he remained until his death. Fortunately, his masterwork on the sizes and distances of the Sun and Moon has survived, offering an insight into one of the greatest minds of antiquity. Before launching into the calculations, let me summarize our method. Our method will be based on 5 observations, each of which will reveal a geometric relationship. The combination of these relationships will allow us to determine the distance to the Sun and Moon. The first observation, that of a half-moon, will allow us to determine the distance to the Sun in terms of the distance to the Moon. Our second observation, that of a total solar eclipse, will allow us to determine the diameter of the Sun in terms of the diameter of the Moon. Our third observation, that of a lunar eclipse, will allow us to determine the diameter of the Sun in terms of the diameter of the Earth, as well as the diameter of the Moon in terms of the diameter of the Earth. Our fourth observation, that of a full moon, allows us to determine the distance of the Moon in terms of the diameter of the Moon. The fifth observation, that of a shadow cast by a stick, was used by Eratosthenes, another ancient Greek, to determine the diameter and circumference of the Earth, and we are going to use his approach to determine the diameter of the Earth in kilometers. Once we know the diameter of the Earth in kilometers, we can then determine the diameter of the Sun and Moon in kilometers, as well as the distance to the Sun and Moon in kilometers, and our task will be complete. The first calculation of Aristarchus was based on the observation of a half-moon, as represented in the diagram. In particular, Aristarchus realized that the line connecting the centre of the Earth with the centre of the Moon, and the line connecting the centre of the Moon with the centre of the Sun, makes an angle of 90 degrees. And therefore we can focus in on this right-angled triangle formed by connecting Earth, Sun and Moon. Furthermore, dm represents the distance between the Earth and the Moon, and ds represents the distance between the Earth and the Sun. Aristarchus realized that he would be able to determine a relationship between the distance to the Sun and the distance to the Moon if he was able to measure the angle theta. At the time, the best measurement of theta was around 87 degrees. But I'm going to use the modern day value, which is closer to 90. In fact, modern day measurements give a value of theta equal to 89.853 degrees. Once we know theta, we can then use trigonometry to determine the relationship between ds and dm. Here we have a right-angled triangle, and we know that for a right-angled triangle, cos of theta is equal to the adjacent divided by the hypotenuse. In our particular example, the adjacent side is represented by dm and the hypotenuse is represented by ds, and so we may write cos theta equals dm divided by ds. If we now rearrange this expression so that we have ds divided by dm, then this is going to be clearly equal to 1 divided by cos theta. If we now substitute in our value for theta, we have 1 divided by cos of 89.853. And if you put this into your calculator, you find that ds divided by dm is equal to roughly 390. This tells us that the Sun is roughly 390 times further away from Earth than the Moon is. And this ends our first calculation. The second calculation of Aristarchus is based on the observation of a total solar eclipse. A total solar eclipse occurs when the Moon moves between the Earth and the Sun, causing a shadow to be cast on part of the Earth as you can see in the diagram. I'd like you to pay particular attention to two features of this diagram. The first is the small triangle formed by the lines connecting the centre of the Earth with the centre of the Moon with the edge of the Moon, and the edge of the Moon with the centre of the Earth. This is a right-angled triangle. The second feature is the larger right-angled triangle formed by connecting the centre of the Earth with the centre of the Sun with the edge of the Sun, and the edge of the Sun with the centre of the Earth. Notice that the smaller right-angled triangle is contained within the larger right-angled triangle, and this tells us that these two triangles are similar. That simply means that the ratio of the two triangle base lengths, dm and ds, that ratio is the same as the ratio of the two triangle heights, rm and rs, and therefore we can write ds divided by dm equals rs divided by rm. Now clearly the ratio of the radii, rs divided by rm, is going to be the same as the ratio of the diameters, ds divided by dm, because the diameter is simply twice the radius. We saw in our previous calculation that the distance to the Sun divided by the distance to the Moon is equal to 390, and now we see that this relationship also holds for the ratio of the diameter of the Sun and the diameter of the Moon. This tells us that the diameter of the Sun is roughly 390 times the diameter of the Moon, and this ends our second calculation. The third calculation of Aristarchus is based on the observation of a lunar eclipse. A lunar eclipse occurs when the Earth casts its shadow on the Moon, as can be seen in this diagram. Our shadow represents the radius of the cast shadow at the location of the Moon. And as previously, dm represents the distance between the Earth-Moon, ds is the distance between the Earth and Sun, rs is the radius of the Sun, and re is the radius of the Earth. Notice that the two shaded triangles are similar, and therefore the ratio ds to dm, which is the ratio of the longer base to the shorter base, is going to be equal to the ratio of the height of the larger triangle to the height of the smaller triangle. So therefore we can write ds divided by dm, which is the ratio of the larger base to the shorter base, is equal to, well, what is the height of the larger triangle? Clearly, the height of this larger triangle is going to be equal to the difference between rs, which is the radius of the Sun, and re, which is the radius of the Earth. And so we can write rs minus re divided by, well, what's the height of the smaller triangle? As you can see, the height of the smaller triangle is going to be the difference between re and r shadow. So we can write re minus r shadow. And as we saw in part 2, the distance to the Sun divided by the distance to the Moon is also equal to the radius of the Sun divided by the radius of the Moon. We're going to now take this expression and rearrange it. In particular, I'm going to divide through by rs on both sides and multiply both sides by re minus r shadow. That's going to then give us the following expression: rs minus re divided by rs equals re minus r shadow divided by rm. We can then simplify this expression. For example, rs divided by rs is going to be 1, so this is going to be equal to 1 minus re over rs equals re divided by rm minus r shadow divided by rm. And then finally I'm going to just write this in a slightly different form by moving this term over to the left hand side and this term over to the right hand side, and that gives us 1 plus r shadow divided by rm is equal to RE divided by RM plus RE divided by RS. Now, it had been noted by the ancient Greek astronomers that the radius of the shadow cast by the Earth on the Moon was roughly twice the radius of the Moon. Modern day values suggest that this is actually closer to 2.6 times the radius of the Moon. So we're going to use the fact that our shadow is approximately equal to 2.6 times the radius of the Moon, Rm. And so where you see this expression here, we can just replace it with the number 2.6. So therefore we're going to have 1 plus 2.6 is equal to RE divided by RM plus RE over RS. And therefore we can say that 3.6 is equal to RE over RM plus RE over RS. Now what we can do is you can take this expression and factorize it in two different ways. The first way is by writing 3.6 is equal to, and now we take out a factor of RE over RM, and we can write this as 1 plus Rm over Rs. You can confirm that this is indeed the case by multiplying out this expression, and you see that you will recover this expression over here. What we can then do is divide both sides by this bracket term, and that's going to give us 3.6 divided by 1 plus Rm over Rs equals Re divided by Rm. And now notice what happens. We can actually substitute in a value Rm over Rs because we calculated that in one of the previous parts, where we determined that the radius of the Sun divided by the radius of the Moon is approximately 390. And so clearly the radius of the Moon divided by the radius of the Sun is going to be approximately 1 divided by 390. And so we see that Re over Rm is equal to 3.6 divided by 1 plus 1 over 390. And this number on the bottom is very close to 1. And so we see that this is roughly equal to 3.6. And so this calculation tells us that the radius of the Earth is roughly 3.6 times the radius of the Moon. Now we could also have factorized this expression in a different way. Let's now look at that. We can write 3.6 equals Re divided by Rs bracket Rs over Rm plus 1. Now if you multiply out this expression, you see that you will recover that expression over there. And therefore we can write 3.6 divided by Rs over Rm plus 1 equals Re divided by Rs. And again, we can put in the numbers because we know that Rs divided by Rm is 390. And therefore we're going to have 3.6 divided by 390 plus 1, which is 391. So this is going to be 3.6 divided by 391. And now if we flip both sides, this fraction and this fraction, we can write Rs divided by Re is equal to 391 divided by 3.6, and that's approximately equal to 109. And so now you see that we have an expression for the radius of the Sun in terms of the radius of the Earth. Namely, the radius of the Sun is approximately 109 times the radius of the Earth. So these two results, Re over Rm equals 3.6 and Rs over Re equals 109, end our calculations in part 3. Our fourth calculation is based on the observation of a full moon, as represented by this diagram. If you take two lines from either side of the moon and connect those to an observer on Earth, then the angle between the two lines can be measured, and the modern day value is around 0.519 degrees. We can use this information along with the fact that the diameter of the moon, dm, provides an approximation to an arc which forms part of a circle of radius dm. We can then use this information to write the ratio 0.519 divided by 360. In other words, the ratio of this small angle to the number of degrees in a full circle is going to be equal to the ratio dm, which represents the small arc, to the circumference of a circle of radius dm. And as we know, the circumference of a circle is equal to 2 times pi times the radius, which in our case is dm. And so just by using the symmetry and geometry of our diagram, we can write this result. A simple rearrangement then gives us the expression dm divided by little dm equals 2 pi times 0.519 divided by 360, and if you put that into your calculator you find a value of 0.009. We can now use this result to determine the distance of the Sun in terms of the diameter of the Earth, as well as the distance of the Moon in terms of the diameter of the Earth. In particular, note that if we write the distance of the Sun divided by the diameter of the Earth, little ds divided by big de, we can rewrite this as ds divided by de multiplied by ds divided by big ds. Notice that you can equate both of these sides. The big ds's cancel and you recover little ds divided by big de, which is what you have on the left hand side. Next, recall from part 2 that the distance of the Sun divided by the distance of the Moon is equal to the diameter of the Sun divided by the diameter of the Moon, and therefore we can write the distance of the Sun divided by the diameter of the Sun is equal to the distance of the Moon divided by the diameter of the Moon. And so over here, where we have the distance of the Sun divided by the diameter of the Sun, we can equivalently replace that with the distance of the Moon divided by the diameter of the Moon. And so we have the distance of the Sun divided by the diameter of the Earth is equal to the diameter of the Sun divided by the diameter of the Earth multiplied by the distance of the Moon divided by the diameter of the Moon. And we just saw a few moments ago that the diameter of the Moon is approximately equal to 0.009 times the distance to the Moon. And so what we can do is we can rewrite this expression ds divided by de multiplied by, well, little dm divided by big dm is going to be 1 divided by 0.009. So if we now put in our values, ds divided by de, well, we saw in part 3 that's approximately equal to 109. So we can write this as 109 times 1 divided by 0.009. Putting in these numbers, we get a value of close to 12,000. And so we see that the distance to the Sun divided by the diameter of the Earth is approximately 12,000. And this is telling us that the Sun is approximately 12,000 Earth diameters away. The other thing that we can do is we can calculate the distance to the Moon in terms of the diameter of the Earth. And to do that, we simply write little dm divided by big de is equal to 1 divided by de divided by dm. And then we can write this as 1 divided by diameter of Earth divided by diameter of moon multiplied by diameter of moon divided by distance to moon. And we can now put in the values, because again we've seen that dE divided by dm, in other words the diameter of the Earth divided by the diameter of the moon, is approximately 3.6. So we can write 1 divided by 3.6 multiplied by the diameter of the moon divided by the distance to the moon, which we saw was 0.009. And if we put these numbers into our calculator, we find something close to 30.9. And that tells us that the distance to the moon divided by the diameter of the Earth is approximately equal to 30.9. And we can put that in a box. And that ends part 4. And notice that what we have are two expressions for the distance to the Sun and the distance to the Moon in terms of the diameter of the Earth. And so our next step is to try and determine the diameter of the Earth in meters. Our fifth calculation was performed by Eratosthenes to determine the diameter and circumference of the Earth. It had been noted that on June 21st at midday, a stick placed in the ground at Syene cast no shadow, whereas a stick placed in the ground at Alexandria did. Eratosthenes was able to make sense of this observation by assuming the Earth was round. And as you can see in the diagram, if the Earth is round, then it's possible for two sticks to cast different length shadows. In particular, the shadow cast at Alexandria by a stick was used to determine the angle made between the base of the shadow and the top of the stick, and this angle theta was measured to be 7.2 degrees. Eratosthenes realized that if you traced back lines from both of the sticks towards the center of the Earth, then the angle made at the center would also be equal to theta, which is 7.2 degrees. Eratosthenes realized that by performing one more measurement, it would be possible to determine the diameter and circumference of the Earth. Legend has it that he paid somebody to pace out the distance between Syene and Alexandria. In modern day terms, this distance was measured to be 800 kilometers. We now see that 800 kilometers, this distance, forms an arc which forms part of the circumference of the Earth, and likewise 7.2 degrees forms a small angle segment of the entire 360 degrees of the Earth. And therefore we can write 7.2 divided by 360 is equal to 800 kilometers divided by the circumference of the Earth, which will be equal to pi times the diameter of the Earth. Now we can rearrange this expression so that we have the diameter of the Earth is equal to 800 kilometers divided by pi times 7.2 over 360, and if you put that into your calculator, you get a value of roughly 12,730 kilometers, or 12,730,000 meters. And we know that the radius is half of this. And this ends the fifth calculation. Now that we have a value for the diameter of the Earth, 12,730 kilometers, we can now calculate the distance to the Sun and the distance to the Moon in kilometers or meters. Recall that the distance to the Sun was approximately equal to 12,000 times the diameter of the Earth, and so if we replace the diameter of the Earth with our calculated value in kilometers, we find 12,000 multiplied by 12,730, and this gives us a value of about 150 million kilometers to the Sun. And similarly, if we write the distance to the Moon as being equal to 30.9 times the diameter of the Earth, we can see that this is going to give us a value of about 390,000 times the distance of 1 kilometer, or 390,000 kilometers. And so we have been able to use the observations of the ancient Greeks, namely observations of the moon and observations of shadows cast by sticks, to calculate the distance of the Sun in kilometres, 150 million kilometres, and the distance of the Moon in kilometres, 390,000 kilometres. I hope you've enjoyed this video, and it's been a great pleasure sharing it.